The most simple and fundamental technique of machine learning is called the Bayesian classifier, and it's also called the naive Bayesian classifier because it makes the assumption that all the features that one uses to learn about historical data are independent for a particular choice of the behavior one is trying to learn. So for example, if one is trying to predict whether a given user is shopping or just surfing using the query words that they use to search, we assume that the words themselves are all independent and equally likely to occur independent of what other words are used in the query. It's not necessarily a valid assumption in most cases, as we have just argued a while back, but that's what's assumed, and that's why it's called the naive Bayes classifier. Anyway, let's try to figure this out from first principles. The probability of B, that is, whether some user is a buyer or just a browser, given the combination of R and C that they use, times the probability of R and C itself. By Bayes' rule, this is nothing but the probability of R and C given B times the probability of B. This is easy to see just by thinking of R comma C as one random variable and just using Bayes' rule. Next, we further expand the first term over here, again using Bayes' rule, forgetting about B for the time being, and noting that the probability of R and C given B is the probability of R given C, and B is there just because it was earlier, times the probability of C given B, which again is there because it was there up there. Again, by applying Bayes' rule, we get this expansion. Now comes the independence assumption. The probability that of R given C, and B or A or whatever else, doesn't matter, because of independence of R and C, is the same as the probability of R given whatever else was there on the conditional side. Because of this independence, we can essentially separately compute these terms: probability of R given by equal to yes, probability of C given by equal to yes, and then just simply multiply it by the a priori, or the overall probability of by equal to yes. We can do the same for by equal to no. So given some values of R and C, that is, whether the word red occurs or the word cheap occurs or not, we compute the probability of R being there, given that by is yes, C being there or not there, given by equal to yes, and the a priori probability of B equal to yes, and divided by the same expression that we have here, but for the other possibility that by equal to a no. Now, since this expression is proportional to the conditional probability that we're looking for, that is, whether or not the user is more likely to be a buyer versus a browser given the query words that they use, we simply compute this ratio for both possibilities, buyer or browser, and if this ratio is greater than 1, in general greater than some threshold, we choose the option by equal to yes as being the most likely estimate. Otherwise, we decide that by equal to no. So, congratulations, we have just derived the most fundamental classification mechanism or machine learning technique called the naive Bayes classifier from first principles. And as you can see, the derivation is simple arithmetic and basic probability. Given any combination of words and the past history, say you have 4 features that we had earlier: red, flower, gift, and cheap, and in general n features, arbitrarily long queries, for example, taking particular values, yes, no, etc., etc., we can merely compute the ratio that we had earlier, simply now that we have n terms in the product as opposed to just 2, and in the end the a priori probabilities of the 2 different types of behavior that we're trying to predict. This ratio is called the likelihood ratio because each of these terms in the product is a likelihood, in the sense that if x1 equal to yes, then the probability here is the probability that x1 equal to yes for the situation when people are buying versus the probability that x1 equal to yes when people are just browsing. And we do that for all the possible words. Many of them will have a no, so xi's for them will be no, but we still have to take all the possible words into account and choose yes if this likelihood ratio is greater than a threshold and no otherwise. We also normally take logarithms to make multiplications into additions, so you would frequently hear the term log likelihood. The reason is because of these many probabilities, all less than 1 being multiplied, you probably will run out of decimal points and you'll get all zeros. So by taking logarithms, you will reduce the chance of such an underflow occurring and make the computation stable. Note in particular that you really need to consider all possible features, even those that don't occur in the query. So if you have 1,000,000 words and your query consists of 4 words, you need to multiply the probabilities for 1,000,000 words. For the 4 words that you have, you'll use the probability that the word occurs for buyers and the probability that the word occurs for browsers. And for the rest, you'll have to include the probabilities that the word does not occur for buyers and for browsers in the denominator. Now this makes it an extremely expensive method, but nevertheless quite useful. The expensiveness we'll figure out how to deal with using parallel computing next week, but for the moment let's take a look at an example of trying to compute sentiment using machine learning and the naive Bayes classifier.